Okay, so, trampolines are... Everybody likes trampolines, right? They're pretty fun. But how do they even work, right? Well, really, it's all about energy. And at the same time, it proves a lot about Newton's laws of motion, which are really worth talking about. So let's get ourselves to a trampoline, and we can talk a little bit about the physics that are going on over there. So let's take our goat over to the... Whoa! Let's take our goat over to the trampoline. Here we go, here we go. Wonderful. We've got a few trampolines here. Great. So, as we were saying before, everybody likes trampolines, but let's try and think about how they work. And let's use them to talk about Newton's laws of motion and also a little bit about energy. Potential energy and kinetic energy are the two, are the reasons trampolines are allow you to jump higher than just on the flat ground, right? So here I am jumping on the ground, and then here I am jumping a little bit higher on the trampoline and getting points for it. So one type of the potential energy that's involved with the trampolines is the potential that's stored in the springs of the trampoline, right? Or the elastic energy. And another type of energy is the gravitational potential energy. Yeah? We've talked about gravitational potential energy before. The higher you are raised above the ground, the more GPE you have. There's also kick energy involved because we've got movement, right? So the equation that would connect all these three things together would be the total energy would equal those potential energies plus the kinetic energy. I'm going to put these equations in the description below. Yeah? There's also some internal energy going on, but that's not really that important here. Yeah? Other things that might be important for explaining what's going on here is thinking about the amount of gravitational potential that we put in is going to be equal to the kinetic energy that we get out of it. Yeah? So if I get myself really high on this... oh, I got my head stuck. There we go. I get myself really high on this diving board here. Yeah, I've got loads of gravitational potential available to me. So that's, of course, going to convert to a ton of kinetic. Right? Oh, I didn't make that. So, so we can think that the total energy is equal to those potentials plus the kinetic, and we can also think that the potential is going to equal our mgh in this case. Yeah, is going to equal our gravitational potential energy, right? We've done this before. We've used mgh to find the potential energy due to gravity. We multiply the mass of the object, or the goat in this case, by the height from the ground. I was really high up before, and we times that by the acceleration due to gravity, which is always 9.81 meters per second So, objects or goats or people with larger masses are going to have greater potential energy due to the acceleration due to gravity for the same height as something with small masses. Right? So like me and this guy here, he's got a bigger mass than me. Let's see if I can get him. Yeah? So, when he's up in the air, he's got more gravitational potential than me. Yeah? However, it's harder for people with larger masses, or objects with larger masses, to reach the same height as people with small masses because the acceleration due to gravity is pulling them down a bit more, as represented in their weight. Now, the potential energy stored in the spring, yeah, can help be determined by something called spring constant. Yeah? K, the spring constant. Now, you can go back and watch some of my videos on Hooke's law, F equals kx, to tell you a little bit about that. The force of the spring is the spring constant, multiplied by how much that spring has changed in length from its compressions of the goat bouncing down on it. Yeah? Now, what's important for this today, what we're talking about, is it demonstrates Newton's third law really nice for us. Because remember, we're trying to talk about the Newton's laws of motion. Every action has an equal and opposite reaction. So when the spring is compressed, yeah, or stretched, the opposite's going to happen. So when the spring's stretched and it's pushing up, and it's going to have to compress again, making the goat jump even higher as the trampoline returns to its original position. Wonderful. Ooh, I can get really high. Oh no. So, because of acceleration due to gravity, larger masses allow the spring to be stretched more, or compressed more. Now that can be shown with F equals ma, yeah? Newton's second law of motion. F is the weight, yeah? Resulting from our mass being times by our acceleration due to gravity, yeah? So when mass increases, so does the weight. This means that the object or person or goat is being pulled down harder than that gravitational field. This stretches the springs of the trampoline more, creating a higher spring potential energy, yeah? But the mass is usually too heavy for the spring to move. So if you just stand, if you just stand there, right? You're not gonna move, yeah? You're gonna need to actually start jumping. Now, smaller kids, you'll notice, will be able to jump higher than adults, even though they have lower potential energy due to gravity. That's because the trampoline can move, yeah? Since they're being pulled down by the gravitational field slightly less. Now, that's all great, a great example of Newton's first law, yeah? Objects in motion are just going to keep on moving, yeah? And objects at rest will not move until acted on by an outside force. The outside forces keep you on the trampoline, are both your weight due to gravity, which keeps you down, and the trampoline itself, which keeps you up. Yeah? And as we said before, you're not going to move until you begin jumping. Pushing your feet down makes you go up. It's Newton's third law. So what we're seeing here is we're seeing all of those Newtonian laws in action. It's really, really pretty incredible. And there's also a lot of stuff we can talk about energy as well, if we want to focus us from an energy perspective. So we'll probably revisit some of these concepts, thinking about energy a little bit later. But all those equations, I'm gonna put those in the description below so you can check those out for yourself. Oh, look, I'm getting pretty high. Woohoo! Oh no, off he goes.